Right now, floating in the cosmic void, there's an absolute beast of a world that has astronomers completely baffled. We're talking about a planet that's so grotesquely massive it makes Jupiter look like a ping-pong ball. Today we're going on a journey to explore the largest planet ever discovered in the universe, a world so gigantic that it sits at the very edge of what we can even call a planet, a cosmic giant that forces us to rewrite the rules. If you're someone who loves exploring the mysteries of space and wants to stay connected to the latest breakthroughs in astronomy, make sure to hit that subscribe button and give this video a like. Now let's get started. When you think of a large planet, you probably picture Jupiter. After all, it's the heavyweight champion of our solar system. You could fit more than 1,300 Earths inside Jupiter's volume. It's a swirling storm of hydrogen and helium, with winds that race at hundreds of miles per hour and a magnetic field so powerful it could be deadly to any spacecraft that ventures too close. Jupiter is massive, but here's the thing that'll blow your mind. Compared to the largest planets we've found beyond our solar system, Jupiter is just a small marble rolling across an endless cosmic floor. The search for worlds beyond our own solar system, what astronomers call exoplanets, began in earnest back in the 1990s. For centuries, humanity could only dream about planets orbiting distant stars. We had theories, we had hopes, but we had no proof. Then, in 1995, everything changed. Two Swiss astronomers, Michel Mayor and Didier Queloz, detected the first confirmed exoplanet orbiting a sun-like star. They called it 51 Pegasi b. This discovery earned them the Nobel Prize in Physics in 2019, and it opened the floodgates. Since that groundbreaking moment, we've discovered more than 5,000 confirmed exoplanets. Think about that number for a second. 5,000 worlds circling distant suns, each one unique. Some are scorching hot, orbiting so close to their stars that their surfaces melt into oceans of lava. Others are frozen ice giants, drifting in the cold outer reaches of their solar systems. There are planets made of diamond, planets where it rains glass sideways, and planets so dark they absorb nearly all the light that touches them. The universe, it turns out, has an imagination far wilder than ours. But among all these bizarre and beautiful worlds, there's a special category that captures our attention: the super-Jupiters. These are gas giants that make Jupiter look tiny. We're talking about planets with masses ranging from several times Jupiter's mass all the way up to the very threshold of becoming something else entirely. Something called a brown dwarf, which is like a failed star. These objects sit in a strange twilight zone between planets and stars, and understanding them helps us answer one of astronomy's most fundamental questions. Where do we draw the line between a planet and a star? To understand why this question matters, you need to know a bit about how stars work. Stars shine because they fuse hydrogen atoms in their cores, creating helium and releasing enormous amounts of energy in the process. This fusion is what makes stars bright and hot. Planets, on the other hand, don't have enough mass to trigger this nuclear fusion. They might generate some heat from their formation or from gravitational compression, but they're not burning fuel like stars do. Brown dwarfs fall somewhere in between. They're too massive to be planets, but not massive enough to sustain hydrogen fusion like a true star. Some brown dwarfs can fuse deuterium, a heavier form of hydrogen, but that's a temporary phase. They're often called failed stars because they never quite made it to full stellar status. The International Astronomical Union, the organization that officially names celestial objects and defines astronomical terms, set a mass limit for planets. According to their definition, a planet can't be more than 13 times the mass of Jupiter. Beyond that threshold, an object is likely massive enough to fuse deuterium, which pushes it into brown dwarf territory. But here's where things get complicated. NASA's Exoplanet Archive uses a different cutoff. They consider objects up to 30 Jupiter masses as potential planets, as long as they orbit a star. This difference in definitions creates some ambiguity, and it's part of what makes the hunt for the largest planet so fascinating. So, what is the largest planet ever discovered? The answer depends on who you ask and how you measure size. Are we talking about mass, which tells us how much stuff is packed into an object, or are we talking about radius, which tells us how physically big it is? Both measurements matter, but they tell us different things. A planet could be incredibly massive, but compressed into a relatively small volume if it's made of dense materials. Conversely, a planet could be less massive, but puffed up like a balloon if it's made of light gases and heated by its star. Let's start with mass. One of the most massive exoplanets ever confirmed is ROXs 42b. Yes, that's its actual name. Astronomy naming conventions can be a bit clunky, but stick with me. ROXs 42b orbits a binary star system in the Rho-Ophiuchi cloud complex, a region of space about 470 light-years away from Earth. This planet, or planetary mass object, as some scientists prefer to call it, weighs in at about 9 to 13 times the mass of Jupiter. That puts it right on the edge of the brown dwarf boundary. What makes ROX 42b so intriguing isn't just its mass, it's how far it orbits from its host stars. This world is located roughly 157 astronomical units away from its parent stars. 1 astronomical unit is the distance between Earth and the Sun, so we're talking about a planet that's more than 150 times farther from its stars than we are from ours. That's an enormous distance. For comparison, Neptune, the outermost major planet in our solar system, orbits at about 30 astronomical units from the Sun. At such a vast distance, ROX 42b takes nearly 2,000 years to complete just one orbit around its stars. Imagine that. A single year on this planet lasts longer than all of recorded human history. This extreme orbital distance raises questions about how the planet formed. Did it coalesce out of a disk of gas and dust like most planets? Or did it form more like a binary star companion through gravitational collapse? The truth is, scientists are still debating this. Recent observations from the James Webb Space Telescope, humanity's most powerful observatory in space, have given us new clues. In February of 2026, just weeks ago, astronomers published findings showing that massive gas giants like those in the HR 8799 system contain sulfur in their atmospheres. Sulfur is a chemical signature that suggests these worlds formed through core accretion, the same process that built Jupiter. In core accretion, a solid core of rock and ice forms first, and then it gravitationally attracts a thick envelope of gas. Finding sulfur in the atmospheres of super-Jupiters tells us that even these gigantic worlds may have started as rocky cores before ballooning into the monsters we see today. This discovery shocked astronomers because it challenges older models. Many scientists thought that objects as massive as 10 or more Jupiter masses couldn't form through core accretion. They believed those worlds must form through gravitational instability, where a clump of gas in a protoplanetary disk simply collapses under its own weight. But the presence of sulfur suggests otherwise. It means that planets can grow much larger through the traditional planet-building process than we ever imagined. ROXs 42b was discovered back in December of 2013 by 2 independent teams of astronomers using some of the world's most advanced telescopes. The Keck Observatory in Hawaii, the Very Large Telescope in Chile, and the Subaru Telescope in Japan all contributed to confirming this massive world's existence. The planet was detected using a method called direct imaging, which is exactly what it sounds like. Instead of inferring a planet's presence by watching a star wobble or dim, astronomers actually took pictures of the planet itself. Direct imaging is incredibly difficult. Planets don't emit much light on their own, and they're drowned out by the glare of their host stars. It's like trying to spot a firefly hovering next to a searchlight from miles away. To overcome this, astronomers use special instruments called coronagraphs that block out the star's light, allowing them to see the faint glow of the planet. ROXs 42b is detectable because it's still young and hot, emitting infrared radiation left over from its formation. The planet has a temperature of around 2,240 Kelvin. To put that in perspective, that's about 3,570 degrees Fahrenheit, or nearly 2,000 degrees Celsius. Hot enough to glow a dull red if you could see it with your own eyes. When astronomers analyzed the light coming from ROX 42b, they found that its atmosphere is thick with clouds and dust. This makes sense for a young gas giant. As planets age and cool, their atmospheres can clear up, but in the early stages, they're turbulent and hazy. The planet's radius has been estimated at about 2.1 times the radius of Jupiter, though there's some uncertainty in that measurement. Determining the size of a distant exoplanet requires sophisticated modeling and assumptions about atmospheric composition, so the numbers can vary depending on the methods used. Another contender for the title of largest planet is HR 2562b. This gas giant orbits a young star located about 33 light-years away from Earth in the constellation Puppis. HR 2562b has a mass estimated at around 30 times that of Jupiter, which actually pushes it well into brown dwarf territory according to most definitions. But because it orbits a star, and likely formed in a protoplanetary disk, some catalogs still list it as an exoplanet. This ambiguity highlights just how blurry the line between massive planets and brown dwarfs can be. What's fascinating about HR 2562b is that it's part of a growing collection of directly imaged worlds that are helping us understand planetary system architectures. By studying where these massive companions are located and how they interact with their host stars, we can piece together the story of how solar systems evolve over billions of years. Every new discovery adds another piece to the puzzle. But we can't talk about the largest planets without mentioning some of the biggest by physical size, not just mass. One of the most extreme examples is a planet called WASP-17b. This world orbits a star about 1,000 light-years from Earth, and it's what astronomers call a hot Jupiter. Hot Jupiters are gas giants that orbit extremely close to their stars, completing an orbit in just a few days. The intense heat from the nearby star causes their atmospheres to puff up like a balloon, making them enormous in volume, even if they aren't the most massive. WASP-17b has a radius nearly twice that of Jupiter, making it one of the physically largest exoplanets known. Its density is incredibly low, similar to styrofoam. If you could somehow find a bathtub big enough, this planet would float. The reason for its inflated size is still being studied, but scientists believe that the star's radiation heats the planet's atmosphere, causing it to expand outward. Some models suggest that energy from the star penetrates deep into the planet's interior, preventing it from cooling and contracting as it normally would. Discoveries like these remind us that planets come in varieties we never anticipated. Before we found exoplanets, all we had to work with was our own solar system. We assumed that other planetary systems would look more or less like ours, with small rocky planets close to the star and gas giants farther out. But the universe had other plans. We've found hot Jupiters scorching in tight orbits, super-Earths larger than our planet but smaller than Neptune, ice giants in blistering deserts, and now these super-Jupiters that blur the boundaries of what a planet even is. Each of these discoveries teaches us something profound about the nature of planetary formation and evolution. They force us to expand our thinking, to question our assumptions, and to remain humble in the face of cosmic complexity. And that's what makes astronomy so thrilling. We're not just collecting data points. We're rewriting the story of how worlds are born. Now, when we talk about these massive planets, it's worth taking a step back to appreciate the bigger picture. Planets don't exist in isolation. They're part of a cosmic hierarchy that stretches from the tiniest grains of dust to the most gargantuan stars imaginable. Understanding where planets fit in this hierarchy helps us grasp just how special and how ordinary they truly are. Let's start small and work our way up. At the bottom of the scale, we have dust and gas. These are the raw materials of the universe, forged in the hearts of dying stars and scattered across space by supernova explosions. Over millions of years, gravity pulls this material together into clumps. As these clumps grow, they heat up from the pressure of all that mass pressing inward. Eventually, if conditions are right, you get a protoplanetary disk, a swirling disk of material orbiting a young star. Within this disk, particles begin to stick together. Dust grains collide and merge, forming pebbles. Pebbles become boulders. Boulders become planetesimals, objects the size of mountains or small moons. Through countless collisions over millions of years, these planetesimals build up into protoplanets and finally into fully formed planets. This process, called accretion, is how Earth formed. It's how Mars, Venus, and Mercury formed. And it's how the cores of gas giants like Jupiter and Saturn came to be. But here's where things get interesting. Once a protoplanet grows large enough, somewhere around 10 times the mass of Earth, its gravity becomes strong enough to start pulling in gas from the surrounding disk. If there's enough gas available, and the planet is far enough from the star that the gas hasn't been blown away, the planet can rapidly accumulate a thick atmosphere of hydrogen and helium. This runaway gas accretion is what transforms a rocky core into a gas giant. The amount of gas a planet can accumulate depends on several factors. How much material is in the disk? How quickly is the star blowing gas away with its stellar wind? How far is the planet from the star? And critically, how much time does the planet have before the disk dissipates? Most protoplanetary disks only last a few million years before the gas is either accreted onto planets, blown away by the star, or dispersed into space. So there's a narrow window of opportunity for a planet to become a gas giant. For the truly massive planets we've been discussing, the ones that push into brown dwarf territory, scientists debate whether they all formed this way. Some may have formed through gravitational instability, where a dense region of the protoplanetary disk simply collapses under its own weight, similar to how stars form. This process can happen much faster than core accretion, potentially creating massive objects in just a few thousand years. The challenge is figuring out which formation pathway a particular object took, especially when we're looking at worlds hundreds or thousands of light years away. This brings us to an important point about the nature of discovery in astronomy. When you hear that scientists have discovered the largest planet ever found, it's easy to imagine that they've settled all the questions about that object. But the truth is messier and more exciting than that. Every discovery opens up new mysteries. We find an answer, and it spawns 10 more questions. That's not a bug in the scientific process. That's a feature. It's what keeps us pushing forward, building better instruments, developing new theories, and venturing deeper into the unknown. Take ROXs 42Bb, for instance. We know its approximate mass and size. We've measured its temperature and analyzed its atmospheric composition, but we still don't know for certain how it formed. We don't know if it has moons, though given its mass, it very well could. We don't know what its interior structure looks like or whether it has a solid core beneath all that gas. These are questions that future observations might help us answer, but they require patience and increasingly sophisticated technology. Speaking of technology, let's talk about the tools that make these discoveries possible. The telescopes and instruments we use to study exoplanets are marvels of engineering, representing decades of innovation and collaboration among scientists, engineers, and institutions around the world. Each new generation of telescopes pushes the boundaries of what we can see and measure, bringing us closer to understanding the true diversity of worlds in our galaxy. Ground-based telescopes like the Keck Observatory in Hawaii use massive mirrors to collect light from distant objects. The Keck telescopes have primary mirrors 10 meters in diameter, made up of 36 hexagonal segments that work together as a single reflective surface. The larger the mirror, the more light you can gather, and the fainter the objects you can detect. To image exoplanets directly, these telescopes use adaptive optics, a technology that compensates for the blurring effects of Earth's atmosphere. A laser beam is shot into the sky, creating an artificial star. By measuring how the atmosphere distorts this artificial star, computers can rapidly adjust the telescope's mirror to counteract the distortion, producing sharper images. The Very Large Telescope in Chile is actually an array of 4 separate telescopes, each with a primary mirror 8.2 meters across. These telescopes can work together, combining their light to achieve even greater resolution. This technique, called interferometry, allows astronomers to see details that would be impossible with a single telescope. The VLT has been instrumental in discovering and characterizing exoplanets, including several of the massive gas giants we've discussed. Then there's the Subaru telescope, also in Hawaii, with its 8.2-meter mirror. Subaru specializes in wide-field imaging and spectroscopy, making it ideal for surveying large areas of the sky and studying the atmospheres of exoplanets. By spreading the light from a planet into a spectrum, astronomers can identify which chemicals are present in its atmosphere based on which wavelengths of light are absorbed or emitted. This is how we know that ROX 42Bb has a cloudy, dusty atmosphere, and it's how we're beginning to map the chemical compositions of worlds hundreds of light years away. but ground-based telescopes have limitations. No matter how advanced your adaptive optics are, Earth's atmosphere will always impose some constraints. That's why space telescopes are so valuable. Above the atmosphere, you get a clear, unobstructed view of the universe. And no space telescope has had a bigger impact on exoplanet science in recent years than the James Webb Space Telescope. Launched on Christmas Day in 2021, the James Webb Space Telescope, or JWST, is the most powerful observatory ever sent into space. Its primary mirror is 6.5 meters across, made up of 18 hexagonal segments coated in a microscopically thin layer of gold. Gold is excellent at reflecting infrared light, which is the wavelength range where JWST operates. Infrared is perfect for studying exoplanets because many of them emit most of their energy in the infrared, and infrared light can penetrate dust clouds that would block visible light. JWST orbits the Sun at a point called the second Lagrange point, or L2, about 1.5 million kilometers from Earth. At this location, the gravitational forces of the Earth and Sun balance out, allowing the telescope to maintain a stable position with minimal fuel consumption. A giant sun shield the size of a tennis court keeps the telescope's instruments cold, which is essential for detecting faint infrared signals without being overwhelmed by the telescope's own heat. In just the few years since it began operations, JWST has revolutionized our understanding of exoplanet atmospheres. It's detected carbon dioxide, methane, water vapor, and sulfur compounds in the atmospheres of distant worlds. It's studied hot Jupiters, warm Neptunes, and even some rocky planets. The discovery that massive superjupiters contain sulfur, which I mentioned earlier, came from JWST observations published in February 2026. This finding strongly suggests that these giants formed through core accretion, the same process that built smaller gas giants like Jupiter. What's remarkable is how JWST's observations are challenging our theoretical models. Before we had detailed atmospheric data, scientists built computer simulations to predict what exoplanet atmospheres should look like. Some of those predictions turned out to be accurate, but many were wrong. The universe is more complex than our models anticipated. That's not a failure. It's an invitation to refine our theories, to dig deeper and to keep learning. Understanding massive planets also helps us understand the other end of the cosmic scale. Just as these superjupiters sit at the boundary between planets and brown dwarfs, they also help us understand the lower mass limit for stars. You see, the universe is full of hierarchies and thresholds, and studying objects at the boundaries teaches us about the fundamental physics that governs how matter behaves. If you're curious about the upper limits of stellar mass, I actually made a video exploring the largest star ever discovered in the universe. It's a fascinating journey into objects so enormous they make our sun look like a grain of sand. I'll leave the link in the description and in the comments. Now let's bring this back to the human element, because that's what makes all of this so meaningful. We are storytelling creatures. We look up at the stars and we wonder. We ask questions. We build myths and legends to explain what we see. For thousands of years, those stories were all we had. But now, in this remarkable moment in history, we have the tools to actually go out and explore. We can measure the masses of planets orbiting stars so distant that their light takes centuries to reach us. We can analyze the chemical composition of atmospheres we'll never visit. We're living in an age of discovery that would have seemed like magic to our ancestors. And here's the beautiful part. Every single one of these discoveries, from the smallest exoplanet to the largest superjupiter, tells us something about our own origins. The atoms in your body were forged in the cores of massive stars that exploded billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stellar furnaces. You are literally made of stardust. And when you look up at the night sky, you're not just observing the universe. You're looking at your cosmic family tree. This connection goes even deeper when you consider how rare and precious our own planet is. Earth is a small, rocky world with liquid water on its surface, a protective magnetic field, and an atmosphere that shields us from harmful radiation. As far as we know, it's the only place in the universe where life exists. We've found thousands of exoplanets, but we haven't yet found another Earth. We've found hot Jupiters and ice giants, lava worlds and gas giants, but nothing quite like home. That doesn't mean we're alone. The universe is vast beyond comprehension, with hundreds of billions of galaxies, each containing hundreds of billions of stars. The odds that Earth is the only world hosting life seem vanishingly small, but it does mean that what we have here is special. It means we should cherish it, protect it, and recognize our responsibility as stewards of this pale blue dot. Studying massive exoplanets might seem disconnected from our daily lives, but it's not. It's part of a larger quest to understand our place in the cosmos. It's about pushing the boundaries of human knowledge, satisfying our innate curiosity, and reminding ourselves that we're capable of incredible things when we work together. The telescopes we've built, the data we've collected, the theories we've developed, these are collective human achievements. They represent the best of what we can be. Let's dive deeper into what these massive planets can teach us about the architecture of planetary systems. When we look at our own solar system, we see a certain structure. The small, rocky planets like Mercury, Venus, Earth, and Mars orbit close to the Sun. The gas giants Jupiter and Saturn sit in the middle regions, and the ice giants Uranus and Neptune occupy the outer reaches. This arrangement isn't random. It reflects the conditions that existed in our protoplanetary disk 4.6 billion years ago. Close to the Sun, temperatures were too high for volatile compounds like water, methane, and ammonia to condense into solid ice. Only materials with high melting points, like metals and rocky silicates, could remain solid. That's why the inner planets are small and dense. Farther out, beyond what astronomers call the frost line or snow line, temperatures dropped low enough for water ice to form. This dramatically increased the amount of solid material available for planet building. With more building blocks available, planets could grow larger, eventually becoming massive enough to capture thick atmospheres of hydrogen and helium before the protoplanetary disk dispersed. This model worked well for explaining our solar system, but then we started finding exoplanets, and everything got turned upside down. The very first exoplanet discovered around a Sun-like star, 51 Pegasi b, was a hot Jupiter orbiting insanely close to its star. It completed an orbit in just 4.2 days. This shouldn't have been possible according to our models. Gas giants need to form beyond the frost line where there's enough material to build them. But 51 Pegasi b was practically skimming its star's surface. The solution to this puzzle revolutionized planetary science. Planets don't necessarily stay where they form. They can migrate inward or outward through interactions with the protoplanetary disk or with other planets. 51 Pegasi b probably formed farther out and then spiraled inward, either pulled by gravitational interactions with the disk or nudged by encounters with other planets. This process, called planetary migration, is now understood to be common, perhaps even the norm rather than the exception. Hot Jupiters, like 51 Pegasi b, teach us that planetary systems are dynamic, evolving environments. Planets aren't static objects locked in fixed orbits. They push and pull on each other. They exchange energy and angular momentum. Sometimes they get ejected from their systems entirely, becoming rogue planets drifting alone through interstellar space. Other times, they crash into their stars or collide with each other in catastrophic impacts. The story of a planetary system is one of chaos, violence, and eventual settling into some kind of equilibrium. The massive superjupiters we've been discussing add another layer to this story. Many of them orbit at enormous distances from their host stars, like ROX 42Bb with its 157 astronomical unit orbit. How did they get there? Did they form in place through gravitational instability in the outer regions of the protoplanetary disk? Or did they form closer in through core accretion and then get scattered outward by gravitational interactions with other massive planets? Both scenarios are possible, and the answer probably varies from system to system. One way to investigate this is by looking at entire planetary systems, not just individual planets. The HR 8799 system is a perfect example. This star, located about 130 light-years from Earth in the constellation Pegasus, hosts at least 4 confirmed giant planets. All 4 are massive, ranging from roughly 5 to 10 times the mass of Jupiter. And all 4 have been directly imaged, which is extraordinarily rare. Most exoplanets are detected indirectly through techniques like the transit method or radial velocity measurements. Actually taking pictures of planets is incredibly challenging, but the HR 8799 system is young, and its planets are still glowing with heat from their formation, making them bright enough to photograph. What makes this system so interesting for our discussion is that recent JWST observations detected sulfur dioxide and other sulfur compounds in the atmospheres of these planets. As I mentioned earlier, sulfur is a smoking gun for core accretion. It tells us that these planets formed with solid cores that accumulated gas, rather than forming like stars through direct collapse of gas clouds. But here's what surprised scientists. These planets are so massive and orbit so far from their star that many models suggested they should have formed through gravitational instability, not core accretion. The presence of sulfur forces us to reconsider those models. It means that core accretion is a more robust and flexible process than we thought. Planets can grow much larger through this mechanism, and they can do so even in the outer regions of protoplanetary disks, where the material is more spread out. This has profound implications for understanding how common different types of planetary systems might be and what kinds of worlds we should expect to find as our telescopes become more powerful. Another fascinating aspect of studying these massive planets is what they tell us about the diversity of planetary system architectures. Not every star has planets. Some stars are solitary. Others have planetary systems that look nothing like ours. There are systems with multiple hot Jupiters, which shouldn't be stable according to simple models but somehow persist. There are systems with planets in highly elliptical orbits that swing from scorching heat to frozen cold. There are systems where planets orbit in the opposite direction of their star's rotation, suggesting violent scattering events in their past. One of the most intriguing configurations is circumbinary planets, worlds that orbit around binary star systems. Remember ROX 42BB? It orbits a binary star. Imagine standing on the surface of such a world if it had a surface. You'd see 2 suns in the sky, maybe one large and bright, the other smaller and dimmer. As they orbited each other, they'd create complex patterns of light and shadow. The planet's climate would be incredibly complicated, with heating patterns that varied depending on the positions of both stars. Circumbinary planets are common enough that we've detected dozens of them, including some in the famous Kepler-16 system, which astronomers nicknamed the Tatooine system, after the fictional planet in Star Wars. These discoveries show that planets can form and survive in environments we once thought too chaotic for planet formation. Binary stars gravitationally perturb each other, creating fluctuating conditions in the protoplanetary disk. Yet somehow planets still manage to coalesce and thrive. This adaptability of planetary formation processes is one of the most important lessons from exoplanet science. Nature is more creative, more resilient, and more diverse than we ever imagined. The universe doesn't follow our neat categories and assumptions. It does what the laws of physics allow, and those laws permit an astonishing variety of outcomes. Every time we think we understand the rules, we discover an exception that forces us to expand our thinking. Now, let's talk about the future. We've made incredible progress in exoplanet science over the past 3 decades, but we're really just getting started. The next generation of telescopes and instruments promises to take us even further. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter when it begins operations. That's roughly 4 times larger than any optical telescope currently in existence. With that kind of light-gathering power, astronomers will be able to directly image smaller, cooler planets and study their atmospheres in unprecedented detail. NASA is also planning a mission called the Habitable Worlds Observatory, which aims to directly image Earth-like planets around nearby stars and search for signs of life in their atmospheres. This telescope will use a device called a starshade, a giant flower-shaped screen that flies separately from the telescope and blocks out the star's light, allowing the faint light from orbiting planets to be detected. It's an ambitious concept, but if successful, it could revolutionize our understanding of how common habitable worlds are in our galaxy. The European Space Agency's Plato mission, set to launch in 2026, will survey roughly 1 million stars, searching for transiting planets and characterizing their properties. Plato is specifically designed to find Earth-like planets in the habitable zones of Sun-like stars, the regions where temperatures are just right for liquid water to exist on a planet's surface. Combined with follow-up observations from JWST and ground-based telescopes, Plato could help us identify the best targets for detailed atmospheric studies. But even as we push toward finding smaller, more Earth-like worlds, the study of massive planets remains crucial. These giants dominate the dynamics of planetary systems. Their gravity shapes the orbits of smaller planets. They can act as shields, deflecting comets and asteroids that might otherwise bombard inner rocky planets. Jupiter, for instance, has been called Earth's guardian because its massive gravity well captures or deflects many objects that venture into the inner solar system. Without Jupiter, Earth might have suffered far more catastrophic impacts over its history, possibly preventing complex life from ever evolving. Understanding the population of giant planets around other stars helps us predict what kinds of planetary systems are most conducive to the emergence and persistence of life. Do you need a Jupiter-like guardian to protect your habitable worlds? Or can life thrive in systems without gas giants? These are open questions, and studying massive exoplanets is key to answering them. There's also the question of moons. We know that the giant planets in our solar system host extensive moon systems. Jupiter has at least 95 known moons, including the 4 large Galilean moons discovered by Galileo in 1610. Europa, one of these moons, has a subsurface ocean that might harbor microbial life. Saturn's moon Enceladus also has a subsurface ocean, and geysers of water vapor and organic compounds erupt from cracks in its icy crust. These moons are some of the most promising places to search for life in our solar system. If giant exoplanets have similar moon systems, and there's no reason to think they don't, then those moons could be habitable even if the planets themselves aren't. A massive super-Jupiter orbiting in its star's habitable zone could host moons with liquid water oceans, atmospheres, and perhaps even life. We don't yet have the technology to detect exomoons, moons orbiting exoplanets, but scientists are working on techniques that might make it possible in the coming years. Some candidates have already been identified through subtle variations in the timing of planetary transits, though none have been confirmed yet. Imagine discovering not just a massive planet, but an entire system of moons around it, some potentially habitable. That would open up an entirely new category of worlds to explore. Instead of just looking for Earth-like planets, we'd also be searching for Europa-like or Enceladus-like moons. Icy worlds with hidden oceans warmed by tidal heating from their giant planet hosts. The possibilities are staggering. The concept of tidal heating is worth exploring because it reveals yet another way that massive planets shape the environments around them. Tidal heating occurs when a moon or planet is stretched and squeezed by gravitational forces from a nearby massive body. As the object's shape deforms, friction in its interior generates heat. This is why Europa and Enceladus remain geologically active despite being so far from the Sun where temperatures are frigid. Jupiter's immense gravity constantly needs Europa, keeping its subsurface ocean liquid. Saturn does the same for Enceladus. Now imagine a super-Jupiter 10 times more massive than Jupiter. The tidal forces it could exert on nearby moons would be proportionally more intense. Depending on the moon's orbit and composition, this could create environments with vigorous geological activity, volcanic eruptions, and potentially the chemical ingredients necessary for life. But there's a balance. Too much tidal heating and the moon becomes a hellish lava world. Too little and it freezes solid. Somewhere in between lies a sweet spot where conditions might be just right. This is one of the reasons why studying the largest planets matters so much. They're not isolated curiosities. They're linchpins in complex systems of moons, rings, and gravitational interactions. Understanding these systems helps us map out the true diversity of environments where life might emerge. And that's ultimately what drives so much of exoplanet science. We want to know if we're alone. We want to know if life is common or rare. We want to understand what makes a world capable of hosting biology. The search for life beyond Earth is one of humanity's most profound quests. It touches on philosophy, religion, science, and our deepest sense of identity. For most of human history, the question of whether we're alone in the universe was purely philosophical. We could debate it, dream about it, write stories about it, but we had no way to actually investigate it. Now, for the first time, we have the tools to search for answers. We can analyze the atmospheres of distant planets, looking for biosignatures, chemical signs that life might be present. What would a biosignature look like? On Earth, life has dramatically altered our planet's atmosphere. Oxygen makes up about 21% of Earth's atmosphere, and almost all of it comes from photosynthetic organisms like plants and cyanobacteria. Without life constantly replenishing it, oxygen would react with rocks and other chemicals and disappear from the atmosphere in relatively short geological timescales. So if we detected significant amounts of oxygen in an exoplanet's atmosphere, especially alongside other gases like methane that react with oxygen, it would be a strong hint that biological processes might be at work. But detecting biosignatures is incredibly challenging. First, you need to find a planet that's potentially habitable, meaning it orbits in the right temperature zone around its star and likely has a solid surface or liquid water. Then you need to capture enough light from that planet to analyze its atmospheric composition. For small, rocky planets, this is extremely difficult because they're faint and close to their much brighter host stars. It's like trying to detect the chemical composition of a firefly's glow while it sits on a lighthouse beam. This is where massive planets actually help us. Even though they're unlikely to be habitable themselves, they're easier to study because they're larger and often brighter in infrared wavelengths. By perfecting our techniques on giant planets, we learn how to analyze atmospheric spectra, how to distinguish between different chemical compounds, and how to account for various sources of noise and uncertainty. Every massive exoplanet we study is essentially a training exercise for the ultimate goal of characterizing Earth-like worlds. Moreover, as I mentioned earlier, the moons of massive planets could be habitable, and they'd be easier to study than standalone Earth-sized planets because their host planets are so large and bright. We might detect the presence of a moon by watching how it affects the light from the planet, and then we could potentially analyze the moon's atmosphere when it passes in front of or behind the planet. These are sophisticated techniques that require incredible precision, but they're theoretically possible with future instruments. Let's shift gears and talk about another fascinating aspect of massive planets: their internal structure. What's inside a super-Jupiter? We can't see beneath the clouds, but we can make educated guesses based on physics and observations. Gas giants are primarily composed of hydrogen and helium, the two lightest and most abundant elements in the universe. Near the surface, these gases behave more or less like the gases we're familiar with on Earth. But as you descend deeper into the planet, pressure increases dramatically. At depths of a few thousand kilometers below the cloud tops, the pressure becomes so intense that hydrogen transitions into a liquid. Even deeper, at pressures millions of times greater than Earth's atmospheric pressure, hydrogen becomes metallic. Metallic hydrogen is a bizarre state of matter where hydrogen atoms are squeezed so tightly together that electrons break free and flow like electrons in a metal. This gives metallic hydrogen extraordinary properties. It's an excellent conductor of electricity, and the flow of metallic hydrogen in a planet's interior is thought to generate powerful magnetic fields. Jupiter has the strongest magnetic field of any planet in our solar system, nearly 20,000 times stronger than Earth's. This magnetic field extends millions of kilometers into space, creating a magnetosphere that captures charged particles from the solar wind and accelerates them to tremendous speeds. These particles create intense radiation belts around Jupiter that would be lethal to any unprotected spacecraft or astronaut. Jupiter's moons that orbit within the magnetosphere are constantly bombarded by this radiation, which has important implications for their habitability and for future exploration missions. Now imagine a planet 10 or 15 times more massive than Jupiter. Its interior pressures would be even more extreme. There might be exotic phases of matter we've never seen in a laboratory. The magnetic field could be proportionally stronger, creating even more intense radiation environments. And at the very center, there might be a core of rock and ice, squeezed to densities far beyond anything we experience on Earth. Some models suggest that the cores of massive gas giants could contain diamonds the size of mountains, formed from carbon compressed under unimaginable pressure. These interior conditions are relevant to understanding planetary formation and evolution. The ratio of heavy elements to hydrogen and helium in a planet's composition tells us about the environment where it formed. Planets that formed farther from their star, beyond the snow line, should have accreted more ice and rock before capturing their gas envelopes. This would give them larger cores and higher overall metallicities compared to planets that formed closer in. By measuring the masses and radii of exoplanets and comparing them to theoretical models, astronomers can infer these internal properties and piece together the planet's formation histories. One of the most powerful tools for this kind of analysis is measuring a planet's density. Density is mass divided by volume, and it tells you how tightly packed a planet's material is. A planet made mostly of gas will have a low density, while a planet made mostly of rock or metal will have a high density. Jupiter's average density is about 1.3 grams per cubic centimeter, slightly more than water. Earth's density is about 5.5 grams per cubic centimeter because we have a large iron core and a rocky mantle. When we measure the densities of exoplanets, we find an incredible range. Some hot Jupiters are so puffed up by their star's heat that their densities are less than that of styrofoam. Others are surprisingly dense for gas giants, suggesting they have massive cores or unusual compositions. These measurements constrain our models of planetary interiors and help us understand how different formation and evolution pathways produce different outcomes. There's also the question of how planets lose mass over time. Close-in planets, especially hot Jupiters, are subjected to intense radiation and stellar winds from their host stars. This can cause atmospheric escape, where the outer layers of the planet's atmosphere are stripped away and lost to space. Over billions of years, this process can significantly alter a planet's mass and composition. Some planets might start out as gas giants and end up as bare rocky cores, sometimes called chthonian planets, after losing all their gas. We've actually observed planets in the process of losing their atmospheres. Some hot Jupiters have extended clouds of escaping gas that we can detect when the planet transits its star. The atmosphere absorbs starlight at specific wavelengths, creating a signature that reveals not just the presence of the atmosphere, but also its composition and the rate at which it's escaping. These observations provide real-time snapshots of planetary evolution in action. For the most massive planets, atmospheric escape is less of a concern because their gravity is so strong. They can hold on to their atmospheres even in harsh environments. But there are other evolutionary processes at work. Massive planets cool and contract over time. As they radiate away the heat from their formation, their interiors settle into lower energy states and their radii shrink. Measuring the ages and sizes of massive exoplanets helps us calibrate models of this cooling and contraction process. Age determination is its own challenge in astronomy. For individual stars and planets, we often have to rely on indirect methods. If a planet is still in a star-forming region like the Rho-Ophiuchi cloud complex, we can use the age of the region to estimate the planet's age. If the planet orbits a star that's part of a cluster of stars that all formed together, we can use the cluster's age. For older isolated systems, we look at the star's properties, like its rotation rate, activity level, and position on the Hertzsprung-Russell diagram, which relates stellar luminosity and temperature. These methods give us rough age estimates, usually with uncertainties of hundreds of millions or even billions of years. Despite these uncertainties, we've learned that planetary systems span an enormous range of ages. Some of the planets we've discovered are just a few million years old, still glowing hot from their recent formation and embedded in the remnants of their protoplanetary disks. Others are billions of years old, orbiting ancient stars that formed when the universe was young. Studying planets across this age range gives us a timeline of planetary evolution, showing us how worlds change as they age. ROX 42, BB for example, is estimated to be only about 1 to 3 million years old. That's incredibly young by astronomical standards. Earth is 4.5 billion years old, so ROX 42 BB is less than 1,000th the age of our planet. At such a young age, it's still contracting and cooling, which is why it's so luminous in infrared wavelengths. Over the next hundreds of millions of years, it will continue to cool and dim, eventually settling into a more stable configuration. By studying it now, in this youthful phase, we can see processes that occurred in our own solar system billions of years ago, but have long since finished. This is one of the beautiful things about astronomy. We can't watch individual objects evolve because the timescales are too long, but we can observe many objects at different stages of their life cycles and piece together a complete story. It's like walking through a forest and seeing seeds, saplings, mature trees, and fallen logs. You don't have to watch a single tree grow from seed to death to understand the life cycle of trees. You can infer it from the population you observe. The same principle applies to planets. By studying thousands of exoplanets with different masses, sizes, compositions, ages, and orbital configurations, we're assembling a comprehensive picture of how planets form, evolve, and eventually die. And the massive planets, the super-Jupiters at the edge of brown dwarf territory, are critical data points in this picture. They test the limits of our theories. They show us what's possible under extreme conditions. They force us to question our assumptions and refine our models. One of the most intriguing questions about massive planets is whether they play a role in making planetary systems more or less hospitable to life. We've already touched on the idea that Jupiter might act as a protective shield for Earth, deflecting potentially hazardous comets and asteroids. But the relationship between giant planets and the habitability of smaller worlds is more complex than a simple protective effect. In some cases, massive planets can actually make systems more dangerous or chaotic. Consider a scenario where a planetary system has multiple giant planets. These massive worlds exert strong gravitational forces on each other, and over millions of years, their orbits can evolve in unpredictable ways. Sometimes they settle into stable resonances, where their orbital periods are related by simple ratios like 2:1 or 3:2. These resonances can stabilize the system, keeping the planets from colliding or ejecting each other. But in other cases, the gravitational interactions lead to chaos. Planets can be flung into highly eccentric orbits, crossing the paths of other planets and creating havoc. When a giant planet migrates inward through a system, it can scatter smaller rocky planets out of the habitable zone or eject them from the system entirely. It can also disrupt the orbits of asteroids and comets, sending showers of impacts toward the inner system. In our own solar system, there's evidence that Jupiter and Saturn underwent a migration event early in the solar system's history, an event astronomers call the Late Heavy Bombardment. About 4 billion years ago, roughly half a billion years after the solar system formed, the inner planets experienced a spike in impact rates. Craters on the Moon from this period are still visible today. This bombardment would have been catastrophic for any life trying to gain a foothold on early Earth, but paradoxically, it might also have been beneficial. Some scientists think that comets delivered water and organic molecules to Earth during this period, providing the raw materials necessary for life. So the presence of giant planets in a system is a double-edged sword. They can be destructive, but they can also play a role in seeding habitable worlds with the ingredients for life. Understanding these dynamics is crucial as we search for potentially habitable planets. When we find an Earth-sized planet in the habitable zone of a distant star, we need to know what else is in that system. Are there giant planets lurking farther out? If so, are their orbits stable or chaotic? Do they pose a threat to the inner planets, or do they help stabilize and protect them? These are questions that require detailed observations of entire planetary systems, not just individual planets. This is where missions like Plato and future telescopes come in. By surveying large numbers of stars and characterizing their planetary systems, we can start to see patterns. We can identify which types of system architectures are most common and which are most likely to host habitable worlds. We can test our theories about planetary migration, stability, and the role of giant planets in shaping the environments of smaller worlds. Every discovery adds to this growing body of knowledge. Now, let's talk about something that might surprise you. Not all massive planets orbit stars. There are objects called rogue planets, or free-floating planets that drift through interstellar space without any host star. These worlds were either ejected from their birth systems through gravitational interactions or possibly formed in isolation, though that's less likely. Some of these rogue planets are thought to be massive, potentially in the super-Jupiter range. How do we detect rogue planets if they're not orbiting a star? It's incredibly difficult, but not impossible. One method is through gravitational microlensing. This occurs when a massive object passes in front of a more distant star from our perspective. The foreground object's gravity bends and magnifies the light from the background star, creating a temporary brightening that can last days or weeks. By studying the details of this brightening, astronomers can sometimes determine the mass of the lensing object and whether it has planets. Several rogue planet candidates have been discovered through microlensing surveys, though confirming their nature is challenging. Some might be brown dwarfs rather than planets. Others might actually be orbiting stars at very large distances, making them difficult to detect directly. The distinction between a rogue planet and a very wide-orbit planet is somewhat arbitrary. If a planet orbits 10,000 astronomical units from its star, is it really bound to that star in any meaningful way? Or is it effectively an independent object? These free-floating worlds raise fascinating questions. If they're massive enough, they might retain heat from their formation or from radioactive decay in their cores. They might even have atmospheres thick enough to trap this heat, creating subsurface oceans beneath icy crusts. Life on such a world would be incredibly isolated, completely cut off from starlight and living in eternal darkness. But thermochemical energy from the planet's interior could potentially drive ecosystems, similar to the deep-sea hydrothermal vent communities on Earth that thrive without sunlight. The idea of life on a rogue planet might sound like science fiction, but it's within the realm of scientific possibility. Earth's deep-sea vents support complex ecosystems powered entirely by chemical energy. Microbes metabolize hydrogen sulfide and other compounds spewing from the vents, and larger organisms feed on these microbes. There's no reason a similar process couldn't occur in the subsurface oceans of a rogue planet, assuming liquid water exists and there's a source of chemical energy. Detecting life on such a world would be nearly impossible with current technology. We'd have no way to analyze its atmosphere from light years away because the planet emits so little light. We'd need to send a probe, which is far beyond our current capabilities for interstellar travel. But just knowing that such worlds exist and thinking through their potential for habitability expands our understanding of where life might arise. It reminds us that the universe is full of possibilities we haven't even begun to explore. Let's return to the planets that do orbit stars and talk about another aspect of massive planets that's particularly interesting: their weather. Weather on gas giants is nothing like weather on Earth. These worlds have no solid surface, no oceans or continents, just endless layers of gas, swirling and churning in patterns driven by the planet's rotation, internal heat, and radiation from the star. Jupiter's Great Red Spot is probably the most famous example of planetary weather. This enormous storm has been raging for at least several hundred years, possibly much longer. It's so large that you could fit 2 or 3 Earths inside it. Wind speeds at the storm's edges reach up to 680 kilometers per hour. The storm is powered by Jupiter's internal heat and by the complex interactions between different layers of the atmosphere rotating at different speeds. On exoplanets, especially hot Jupiters, the weather can be even more extreme. Because these planets are tidally locked to their stars, one side always faces the star while the other side is in perpetual darkness. This creates enormous temperature differences between the day side and night side, sometimes exceeding 1,000 degrees Celsius. Winds racing from the hot day side to the cold night side can reach supersonic speeds, thousands of kilometers per hour. Some hot Jupiters have atmospheres so hot that rocks and metals vaporize. Silicate clouds form on the cooler night side and then rain down as molten glass. Other planets have clouds of iron droplets or even clouds of corundum, the mineral that forms rubies and sapphires. When astronomers model the circulation patterns on these worlds, they find jet streams that transport heat around the planet, creating complex and ever-changing weather systems. For the most massive planets, those approaching brown dwarf territory, the weather is influenced not just by stellar heating, but also by the planet's own internal heat. These objects are hot enough to glow faintly in infrared wavelengths, and they're actively cooling and contracting. This internal energy source drives convection in the atmosphere, where hot gas rises from the interior, cools at higher altitudes, and then sinks back down. Combined with rapid rotation, this creates banded structures similar to what we see on Jupiter, with alternating zones of rising and sinking gas. Astronomers have even detected weather variations over time on some directly imaged exoplanets. By monitoring changes in brightness and color, they can track storms and cloud patterns as they evolve. Some planets show periodic brightness variations that repeat every few hours, corresponding to the planet's rotation period. These variations might be caused by large storm systems or by patchy cloud coverage rotating in and out of view. It's like watching weather patterns on Earth from space, except these patterns are on worlds hundreds of light years away. Understanding exoplanet weather is important for several reasons. First, it tells us about the physical conditions on these worlds, which constrains our models of atmospheric dynamics and chemistry. Second, weather affects what we observe. Clouds can hide certain atmospheric features or create false signals that complicate our interpretations. When we analyze the spectrum of a planet's atmosphere, we need to account for the effects of clouds, hazes, and weather patterns to accurately determine which chemicals are present. Third, and perhaps most importantly, weather patterns influence habitability. On a potentially habitable planet, the circulation of the atmosphere determines how heat is distributed, how water vapor condenses into clouds and precipitates as rain, and how nutrients are cycled through the environment. A planet with efficient atmospheric circulation might maintain temperate conditions even if it receives uneven heating from its star. A planet with poor circulation might develop extreme temperature gradients that make most of its surface uninhabitable. The massive planets we've been discussing aren't habitable themselves, but studying their weather prepares us for analyzing the atmospheres of smaller, rocky worlds. The same physical principles apply, scaled down to smaller sizes and different compositions. Every atmospheric spectrum we analyze, every cloud pattern we map, every storm system we track adds to our toolkit for eventually characterizing Earth-like exoplanets. There's also an aesthetic dimension to all of this that's worth acknowledging. The images we've captured of exoplanets, though often just dim dots or fuzzy blobs, represent something profound. We're seeing other worlds with our own eyes, or at least with our instruments. Each photon that reaches our telescopes traveled for years, decades, or centuries across the emptiness of space, carrying information about a distant world. When we look at these images, we're not just seeing scientific data. We're witnessing the universe revealing itself to us. This sense of wonder and connection is part of what makes astronomy so meaningful. It's not just about collecting facts or testing theories. It's about satisfying a deep human need to explore, to understand, to connect with something larger than ourselves. When you gaze up at the night sky and realize that some of those stars have planets orbiting them, some of which are larger than anything in our solar system, it changes your perspective. You realize that our corner of the universe, while special to us, is just one small part of an unimaginably vast cosmos. And here's something to ponder. Every single discovery we've made in exoplanet science happened within the span of a single human lifetime. The first exoplanet around a sun-like star was discovered in 1995. That's less than 31 years ago, as of now in 2026. In that short time, we've gone from knowing about only the planets in our solar system to cataloging thousands of worlds across the galaxy. We've seen hot Jupiters and ice giants, super-Earths, and mini-Neptunes, massive planets at the edge of brown dwarf territory and tiny planets smaller than Earth. This explosive growth in our knowledge is accelerating. The James Webb Space Telescope has been operational for less than 5 years and has already revolutionized multiple fields of astronomy. The extremely large telescope will be even more powerful when it comes online. Future missions will push the boundaries further still. Within your lifetime, we might discover definitive evidence of life on another world. We might photograph an Earth-like planet orbiting a nearby star and analyze its atmosphere, seeing the telltale signs of biological activity. These aren't distant dreams. They're realistic possibilities based on current technological trajectories. The rapid pace of discovery brings us to an important point about the nature of scientific progress. Science isn't a straight line from ignorance to knowledge. It's a winding path full of surprises, setbacks, and paradigm shifts. Sometimes we discover something that fits neatly into our existing models, confirming what we suspected. But more often, we find things that challenge our assumptions and force us to rethink fundamental concepts. The discovery of hot Jupiters is a perfect example. Before 1995, our theories of planet formation were based entirely on our solar system. We thought we understood how planets formed and where they should be located relative to their stars. Then 51 Pegasi b shattered those assumptions. A Jupiter-sized planet orbiting its star every 4 days? That wasn't supposed to be possible. Yet there it was, undeniable evidence staring us in the face. The scientific community's response to this discovery is instructive. There was initial skepticism, which is healthy. Extraordinary claims require extraordinary evidence, and the detection methods were new enough that mistakes were possible. But as more hot Jupiters were discovered using independent methods and telescopes, the skepticism gave way to acceptance. Scientists didn't cling to the old models. They adapted, developing new theories about planetary migration to explain these unexpected worlds. This flexibility and willingness to revise theories in light of new evidence is what makes science so powerful. It's self-correcting. Bad ideas eventually get weeded out because they don't match observations. Good ideas survive and get refined. Over time, our understanding becomes more accurate and more complete. But it's never finished. There's always more to learn, always another layer of complexity to uncover. The massive planets we've been discussing are part of this ongoing process of discovery and revision. Each new super Jupiter we find adds to our data set. Each atmospheric analysis reveals unexpected chemicals or properties. Each directly imaged system shows us planetary architectures we hadn't imagined. And with each discovery, we refine our models, adjust our theories, and push our understanding a little bit further. One area where massive planets are particularly valuable is in testing theories of planetary migration. We've talked about how planets can move from where they form to different orbital positions, but let's dig deeper into the mechanisms. There are several different types of migration, each driven by different physical processes. Type 1 migration occurs when a planet is still embedded in its protoplanetary disk. The planet's gravity creates spiral density waves in the disk, similar to how a boat creates waves in water. These waves exert torques on the planet, typically causing it to spiral inward toward the star. For Earth-mass planets, Type 1 migration can be quite rapid, potentially moving a planet from Jupiter's orbit to Earth's orbit in just 100,000 years. This raises a puzzle. If migration is so efficient, why didn't all planets spiral into their stars before the disk dissipated? The answer likely involves feedback mechanisms that slow or reverse migration under certain conditions. For example, if a planet migrates into a region of the disk where the temperature or density changes abruptly, the migration rate can slow or even reverse. There might also be magnetic effects or turbulence in the disk that affect migration rates. These details are still being worked out through computer simulations and observations. Type 2 migration happens when a planet becomes massive enough to carve a gap in the protoplanetary disk. Once the gap forms, the planet becomes locked to the disk's evolution, migrating inward as the disk itself drains onto the star. This type of migration is slower than Type 1, but can still move planets over large distances. Jupiter may have undergone some Type 2 migration early in the solar system's history, though it didn't migrate as far as some exoplanets clearly have. Then there's gravitational scattering, which doesn't involve the disk at all. This occurs when two or more massive planets interact gravitationally, exchanging energy and angular momentum. One planet can be flung into a highly eccentric orbit or ejected from the system entirely, while the other planet moves to a different orbit to conserve momentum. This process can explain some of the weird orbital configurations we see in exoplanetary systems, like planets in extremely elongated orbits or planets orbiting in the wrong direction relative to their star's rotation. The most massive planets, the super Jupiters, are particularly interesting in this context because their large masses make them dominant players in these gravitational interactions. A planet 15 times the mass of Jupiter can dramatically reshape an entire planetary system through scattering events. By studying the current orbital configurations of these massive planets and running computer simulations backward in time, astronomers can sometimes reconstruct the migration history of entire systems. One system that's been studied extensively is Upsilon Andromedae, a star about 44 light-years from Earth that hosts at least 4 planets. The inner 3 planets are all massive, with minimum masses ranging from about half a Jupiter mass to several Jupiter masses. Their orbits are strangely configured, with one planet in a highly eccentric orbit. Computer simulations suggest that this system underwent a violent dynamical history, with multiple planets interacting gravitationally and settling into their current orbits after a chaotic phase. There might have been additional planets originally that were ejected from the system entirely. Cases like Upsilon Andromedae show us that planetary systems can be dynamic and violent places. Our solar system, with its nearly circular orbits and stable configuration, might actually be unusual. Many exoplanetary systems show signs of past chaos, gravitational interactions, and dramatic orbital evolution. This has implications for habitability. A terrestrial planet trying to develop life would face challenges if giant planets are constantly perturbing its orbit, causing drastic climate swings or even ejecting it from the habitable zone. But chaos isn't always destructive. Some simulations suggest that gravitational interactions between planets can actually help establish stable orbital resonances. When planets are in resonance, their gravitational effects on each other become periodic and predictable rather than chaotic. This can stabilize a system that might otherwise be unstable. The TRAPPIST-1 system, which hosts 7 Earth-sized planets, is a beautiful example. All 7 planets are in a chain of orbital resonances, each planet's period related to its neighbor's periods by simple ratios. This resonant configuration likely helps keep the system stable, despite having so many planets packed so closely together. Understanding these dynamical processes is crucial for predicting which types of planetary systems can remain stable over billions of years, long enough for life to potentially emerge and evolve. A system with massive planets on chaotic orbits might be a poor candidate for hosting life. A system with massive planets in stable circular orbits at safe distances might be a much better bet. As we build up statistics on planetary system architectures, we can start to identify the most promising targets for future detailed study. Let's shift focus now to the technology that's making all of this possible. We've mentioned several telescopes, but it's worth appreciating just how remarkable these instruments are. The James Webb Space Telescope, for instance, operates at temperatures just a few dozen degrees above absolute zero. It has to be that cold to detect faint infrared signals without being overwhelmed by its own heat. To achieve this, the telescope sits behind a massive sun shield made of 5 layers of material, each thinner than a human hair. The sun shield blocks heat from the sun, Earth, and Moon, creating a permanent shadow where the telescope's instruments stay cold. The telescope's primary mirror is made of 18 hexagonal segments, each coated with a microscopically thin layer of gold. Gold is used because it's highly reflective in infrared wavelengths, but getting 18 separate mirror segments to work together as a single, coherent optical system is extraordinarily challenging. Each segment can be individually adjusted using tiny motors called actuators, allowing ground controllers to align the mirror with nanometer precision. The entire telescope had to fold up to fit inside the rocket that launched it, then unfold in space like an elaborate piece of origami. The fact that this worked flawlessly is a testament to the skill and dedication of the thousands of engineers and scientists who built it. JWST's instruments are equally impressive. The near-infrared spectrograph, or NIR-SPEC, can simultaneously observe up to 100 objects, capturing spectra for each one. This allows astronomers to efficiently study multiple stars or galaxies in a single observation. For exoplanet science, NIR-SPEC can take detailed spectra of a planet's atmosphere as it transits its star, revealing which chemicals are present based on which wavelengths of light are absorbed. The mid-infrared instrument, or MIRI, operates at even longer wavelengths and requires cooling to just 7 degrees above absolute zero. MIRI uses a special refrigerator system to reach these extreme temperatures.
It's particularly good at studying cooler objects like brown dwarfs and massive planets that emit most of their energy in the mid-infrared.
MIRI can also peer through dust clouds that block visible light, allowing astronomers to observe star-forming regions and the centers of galaxies. Ground-based telescopes have their own impressive capabilities. The Very Large Telescope in Chile uses adaptive optics systems that can make corrections 1,000 times per second, compensating for atmospheric turbulence. The system measures how the atmosphere distorts light from a guide star, then applies opposite distortions to a deformable mirror in the telescope's optical path. The result is images almost as sharp as if the telescope were in space, at least for certain wavelengths and conditions. The upcoming extremely large telescope will take this even further. Its 39-meter primary mirror will be made of 798 hexagonal segments, all working together with adaptive optics to produce unprecedented image quality. The telescope will be able to directly image rocky exoplanets around nearby stars and study their atmospheres. It will probe the early universe, looking at the first galaxies that formed after the Big Bang. And it will investigate countless other mysteries, from the nature of dark matter to the detailed structure of black holes. Building instruments of this scale and sophistication requires international collaboration. The ELT is a project of the European Southern Observatory, which is supported by 16 member countries. JWST was developed by NASA in partnership with the European Space Agency and the Canadian Space Agency. Thousands of scientists, engineers, and support staff from dozens of countries contributed to these projects. This global cooperation represents humanity at its best, working together toward common goals that benefit all of us. The knowledge we gain from these telescopes doesn't just advance astronomy. It drives technological innovation that spills over into other fields. The detectors developed for space telescopes have applications in medical imaging. The data processing algorithms used to analyze astronomical images help improve artificial intelligence and machine learning. The materials science required to build ultra-lightweight space structures benefits aerospace engineering and manufacturing. When we invest in space exploration and astronomy, we're investing in innovation that creates value far beyond the immediate scientific returns. There's also the inspirational value. Images from Hubble and JWST have captivated millions of people around the world, sparking interest in science and inspiring young people to pursue careers in STEM fields. The pale blue dot image taken by Voyager 1 in 1990, showing Earth as a tiny speck in the vastness of space, became an iconic reminder of our fragility and the importance of caring for our planet. The first direct images of exoplanets had a similar impact, making distant worlds tangible and real in people's imaginations. Every generation has its defining scientific achievements. For the 20th century, it was splitting the atom, discovering the structure of DNA, landing humans on the moon, and developing computers. For the 21st century, it might be detecting gravitational waves, imaging black holes, finding life beyond Earth, and unlocking the nature of dark matter and dark energy. The discovery and characterization of exoplanets, including these massive super-Jupiters, is part of this ongoing revolution in our understanding of the universe. As we continue our exploration of these massive worlds, it's important to consider the philosophical implications of what we're discovering. Finding thousands of planets around other stars fundamentally changes our perspective on our place in the universe. For most of human history, Earth was thought to be the center of everything. The sun, moon, planets, and stars all revolved around us. This geocentric view made sense based on everyday observations. The ground feels stationary beneath our feet, while everything in the sky appears to move. Then came Copernicus in the 16th century, proposing that Earth and the other planets orbit the sun. This heliocentric model was revolutionary, literally and figuratively. It displaced humanity from the center of the cosmos. Galileo's telescopic observations in the early 1600s provided strong evidence for the Copernican model, though it took decades for the idea to gain widespread acceptance. The Catholic Church famously forced Galileo to recant his support for heliocentrism, though history vindicated him. The Copernican revolution didn't stop with recognizing that Earth orbits the sun. As our understanding grew, we realized that the sun itself isn't special. It's one star among hundreds of billions in our galaxy. And our galaxy, the Milky Way, is one galaxy among hundreds of billions in the observable universe. Each step in this progression made the universe larger and made humanity's place in it seem smaller and less central. This process, sometimes called the Copernican principle, suggests that we shouldn't assume we occupy a special position in the universe. Earth isn't at the center. The Sun isn't unique. Our galaxy isn't fundamentally different from others. By extension, if there's nothing special about our cosmic neighborhood, then the processes that led to life on Earth should be able to occur elsewhere. The universe should be teeming with life. But here's the puzzle. If life is common, where is everybody? This question, famously posed by physicist Enrico Fermi during a lunch conversation in 1950, is known as the Fermi paradox. Our galaxy is about 13 billion years old. Even if intelligent civilizations are rare, and even if interstellar travel is slow, there's been plenty of time for a civilization to colonize the entire galaxy. Yet we see no evidence of extraterrestrial intelligence, no radio signals, no megastructures around distant stars, no visiting spacecraft. The universe seems eerily quiet. There are many proposed solutions to the Fermi paradox. Maybe life is common, but intelligence is rare. Maybe intelligence is common, but technological civilizations tend to destroy themselves before they can spread to the stars. Maybe interstellar travel is so difficult that civilizations stay confined to their home systems. Maybe advanced civilizations are out there but deliberately avoiding contact with us, waiting for us to reach some threshold of development. Or maybe we're looking in the wrong places or listening for the wrong signals. The discovery of exoplanets doesn't solve the Fermi paradox, but it does provide crucial context. We now know that planets are common. Most stars have them. Many stars have planets in their habitable zones. The raw material for life, the planetary real estate where biology could potentially take hold, is abundant. This makes the silence even more puzzling. If suitable worlds are everywhere, why aren't they producing detectable signs of life? One possibility is that we're asking the wrong question. Maybe life is common, but complex life is rare. On Earth, single-celled organisms appeared relatively quickly after the planet formed, within the first billion years or so. But complex multicellular life took much longer to evolve. For most of Earth's history, roughly 3 billion years, life consisted only of microbes. Complex organisms only emerged about 600 million years ago during the Cambrian explosion. Intelligent life capable of building civilizations appeared just a few 100,000 years ago, an eye blink in geological time. If this pattern is typical, then while microbial life might be common throughout the galaxy, complex life could be extraordinarily rare. And even among worlds with complex life, technological civilizations might be vanishingly rare. Perhaps most biospheres never produce intelligence. Perhaps intelligence usually evolves in forms that don't develop technology. Dolphins and elephants are intelligent, but they don't build radio telescopes. If conditions have to be just right at every step, from planet formation to the emergence of technology using intelligence, then we might be alone in our galaxy even if microbial life is widespread. Alternatively, maybe the window of detectability for technological civilizations is narrow. A civilization might only broadcast radio signals for a century or two before moving on to other communication methods that are harder to detect. They might exist for thousands or millions of years but only be obviously visible for a small fraction of that time. If civilizations are spread out across space and time, we might simply be experiencing cosmic bad luck, existing in a time and place where no other civilization's detectable phase overlaps with ours. These questions about life and intelligence tie directly into our study of exoplanets. Every planet we characterize tells us something about the potential for life. When we find a massive superjupiter, we learn about the planetary system's architecture, which affects the stability and habitability of any smaller planets that might be present. When we analyze an atmosphere and find unexpected chemistry, we expand our understanding of what kinds of environments planets can create. When we discover a planet in the habitable zone, we identify a target for future biosignature searches. The search for life beyond Earth is one of the grand quests of our time. and it's driven by both scientific curiosity and a deep human need to understand our place in the cosmos. Are we alone, or are we part of a vast community of living worlds? The answer has profound implications for how we see ourselves and our responsibilities. If life is rare and precious, perhaps existing on only a handful of worlds in the entire galaxy, then it becomes even more imperative that we protect the life we have here on Earth. We might be the universe's way of understanding itself, rare islands of consciousness in an ocean of lifeless matter. But if life is common, if the universe is alive with countless biospheres and perhaps even other civilizations, then we're part of something larger. We're not isolated or alone. We're participants in a cosmic story that's unfolding across billions of worlds and billions of years. Either answer is profound. Either answer changes everything. Let's bring this back to the massive planets and think about what they specifically teach us about habitability. We've discussed how giant planets can protect inner worlds from impacts or destabilize their orbits. But there's another factor to consider. Giant planets affect the delivery of water and organic molecules to inner planets. In our solar system, the asteroid belt between Mars and Jupiter contains countless rocky and icy bodies left over from planet formation. Gravitational perturbations from Jupiter occasionally send these objects into the inner solar system, where they can impact Earth and the other terrestrial planets. Early in Earth's history, during the period called the Late Heavy Bombardment, the impact rate was much higher than it is today. Some of these impacting objects were comets and water-rich asteroids that delivered water to Earth's surface. This water accumulated over millions of years, eventually forming our oceans. Without this delivery mechanism, Earth might have remained a dry planet, and life as we know it couldn't have emerged. Jupiter's role in this process is complicated. On one hand, its gravity helped scatter objects from the outer solar system inward, contributing to Earth's water supply. On the other hand, Jupiter's presence also prevented the material between Mars and Jupiter from coalescing into another planet. If Jupiter hadn't formed or had been much smaller, we might have had an additional rocky planet in that region, and the asteroid belt as we know it wouldn't exist. When we study other planetary systems, especially those with massive superjupiters, we need to consider these effects. A system with multiple superjupiters on eccentric orbits might have experienced such violent gravitational interactions that most of the small rocky bodies were ejected or destroyed. This could leave inner planets bone dry without the water necessary for life. Conversely, a system with a massive planet in a stable circular orbit at the right distance might have an ideal configuration for delivering water and organics to habitable zone planets. These are the kinds of detailed questions that drive current research. As we characterize more planetary systems and study their architectures, we're building a statistical understanding of which configurations are most conducive to habitability. This will help us prioritize targets for future biosignature searches. Instead of studying every planet in every star's habitable zone, we can focus on systems that have the right combination of factors, stable orbits, appropriate stellar properties, and favorable system architectures. Another consideration is stellar activity. The type of star a planet orbits dramatically affects its prospects for habitability. Most exoplanets discovered so far orbit M dwarfs, also known as red dwarfs, which are small cool stars much dimmer than the Sun. M dwarfs are attractive targets for planet searches because they're common, making up about 70% of all stars, and because their small size makes it easier to detect planets around them. A planet transiting an M dwarf blocks a larger fraction of the star's light than the same planet would block if it were transiting a Sun-like star, making the transit easier to detect. However, M dwarfs have properties that could be problematic for life. They're prone to violent flares, sudden brightening events where the star's luminosity can increase by orders of magnitude in just minutes or hours. These flares emit intense ultraviolet and X-ray radiation that could strip away a planet's atmosphere over time, especially if the planet orbits close to the star as it must to be in the habitable zone of a dim M dwarf. M dwarfs are also more magnetically active than Sun-like stars, creating stellar winds that could erode planetary atmospheres. On the flip side, M dwarfs have extremely long lifespans. A red dwarf can shine for trillions of years, far longer than the current age of the universe. This gives life an enormous amount of time to emerge and evolve, Even if conditions are less favorable than on Earth, the sheer amount of time available might compensate. Life might find ways to adapt to high radiation environments or periodic flares, just as life on Earth has adapted to all sorts of extreme conditions. The presence of massive planets in M-dwarf systems is particularly interesting. Because M-dwarfs are so common, and because massive planets seem to be common in general, there should be many systems combining the two. Studying these systems helps us understand whether the benefits of M-dwarfs, their abundance and longevity, outweigh the potential hazards, their activity, and flaring. If massive planets can shield inner worlds from some of the harmful effects of stellar activity, perhaps through their magnetic fields or by capturing high-energy particles, then M-dwarf systems with giant planets might actually be favorable environments for life. Sun-like stars, or G-type stars like our Sun, seem to offer a good middle ground. They're stable, long-lived enough to allow billions of years for life to evolve, and less prone to violent flaring than M-dwarfs. But they're less common, making up only about 7% of all stars. This rarity means there are fewer G-type stars to search, and the ones that exist are generally farther apart, making detailed studies more challenging. Then there are the hot massive stars, the A-type and B-type stars. These stars are large, bright, and short-lived. They burn through their fuel quickly, shining for only tens or hundreds of millions of years before exhausting their nuclear fuel and dying. This might not be enough time for complex life to evolve. Additionally, these stars emit enormous amounts of ultraviolet radiation that could be harmful to life. However, if massive planets around these stars host habitable moons, the moons might be shielded by the planet's magnetosphere, and they'd receive more gentle heating from the planet's infrared glow than from the harsh stellar radiation. Understanding these stellar factors is crucial for the broader project of assessing habitability across the galaxy. It's not enough to find a planet in the habitable zone. We need to know what kind of star it orbits, what other planets are in the system, what the planet's atmosphere is like, whether it has a magnetic field, whether it has plate tectonics to regulate its climate over geological timescales, and countless other factors. Habitability is complex, depending on a delicate balance of many different variables. This complexity is both daunting and exciting. It's daunting because it means finding life might be harder than we hoped. Even if planets are abundant, the fraction that are truly habitable might be small. But it's exciting because every factor we identify gives us a new avenue for investigation. Every planet we study teaches us something about how these factors interact. We're not just discovering worlds. We're building a comprehensive theory of habitability that will guide our search for life for decades or centuries to come. As we delve further into understanding these massive worlds, it's worth considering the role that serendipity and unexpected discoveries play in advancing science. Many of the most important breakthroughs in astronomy came from observations that weren't looking for what they found. Pulsars, rapidly spinning neutron stars that emit beams of radio waves, were discovered in 1967 by Jocelyn Bell Burnell when she noticed strange, regular pulses in radio telescope data. She wasn't looking for pulsars because nobody knew they existed. The discovery opened up entirely new fields of research into extreme physics and stellar evolution. The cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space, was discovered accidentally in 1964 by Arno Penzias and Robert Wilson. They were trying to eliminate persistent noise from a radio antenna, and eventually realized the noise wasn't coming from their equipment. It was coming from the universe itself, a relic from the earliest moments after the Big Bang. This discovery provided powerful evidence for the Big Bang theory and earned Penzias and Wilson the Nobel Prize. In the context of exoplanets, many discoveries have surprised us. The first planets found around pulsars were completely unexpected. Nobody thought planets could survive the violent supernova explosion that creates a pulsar. Yet there they are, orbiting the pulsar PSRB 1957+12, detected through tiny variations in the pulsar's radio signals. These planets might have formed from debris left over from the supernova, or they might be the remnants of a companion star that was consumed by the explosion. Either way, their existence expanded our understanding of where planets can form and survive. Hot Jupiters, as we've discussed, were another surprise. Super-Earths, rocky planets larger than Earth but smaller than Neptune, were also unexpected. We have nothing like them in our solar system, yet they appear to be one of the most common types of exoplanets. Their prevalence suggests that our solar system might actually be somewhat unusual in lacking planets between Earth's size and Neptune's size. This is a humbling realization. The planetary system we grew up with, the only one we knew for most of human history, might not be representative of typical planetary systems at all. These surprises keep us humble and remind us to stay open-minded. When we make predictions about what we'll find as our technology improves, we should hold those predictions loosely. The universe has consistently proven more creative than our imaginations. Who knows what bizarre types of planets or planetary systems we'll discover in the coming decades? Maybe there are worlds made of diamond or solid metal. Maybe there are planets with multiple moons, each large enough to be planets in their own right if they orbited the star directly. Maybe there are planets in binary or even triple star systems with completely alien sky configurations. One category of objects that blurs the boundary between planets and stars even more than the super-Jupiters we've been discussing is dwarfs. These are the coolest known brown dwarfs, with temperatures below about 500 Kelvin, which is cooler than the hottest lava on Earth. Some dwarfs have temperatures comparable to Earth's, around 300 Kelvin or roughly room temperature. At these temperatures, water vapor can condense into clouds in their atmospheres just like clouds on Earth, though the pressure and composition would be completely different. Dwarfs typically have masses between 5 and 30 times that of Jupiter, firmly in brown dwarf territory. But they're so cool and dim that they're incredibly difficult to detect. Most have been found by infrared surveys like the Wide Field Infrared Survey Explorer, or WISE, which map the entire sky at infrared wavelengths. The coolest dwarf discovered so far has a temperature of around 250 Kelvin, colder than the freezing point of water. If you could somehow visit such an object, it would feel cool to the touch, at least until the crushing gravity and extreme pressure got to you. These ultra-cool brown dwarfs are fascinating laboratories for studying atmospheric chemistry and physics under conditions intermediate between planets and stars. They're not massive enough to fuse hydrogen like stars, but they're more massive than any planet we've found. They generate heat primarily from gravitational contraction and from the decay of residual heat from their formation, similar to giant planets like Jupiter. Understanding brown dwarfs helps us understand massive planets because the same atmospheric processes, cloud formation, circulation patterns, and chemical reactions occur in both. There's also an exciting possibility that some dwarfs might have planets of their own. If a brown dwarf can form from the collapse of a gas cloud, just like a star does, then it might have a protoplanetary disk during its formation. Planets could form in this disk and end up orbiting the brown dwarf. We've already found a few examples of planets around brown dwarfs, though confirming them is challenging because the distinction between a massive planet with a small companion and a binary brown dwarf system can be ambiguous. Imagine a planet orbiting a dwarf. The brown dwarf would glow faintly in infrared wavelengths, providing a dim source of heat and light. If the planet orbited close enough, it might be warm enough to have liquid water despite the feeble illumination. From the planet's surface, the brown dwarf would appear as a dull red orb in the sky, barely visible, casting eerie shadows. The planet would receive no light from any regular star, existing in a twilight state illuminated only by its brown dwarf host. It's a strange scenario, but the laws of physics permit it. These edge cases, planets around brown dwarfs that are almost planets, and super-Jupiters that might be either, highlight the difficulty of classification in astronomy. We like to put things into neat categories: stars, brown dwarfs, planets, moons. But nature doesn't always cooperate. The boundaries between categories are fuzzy, and objects exist along a continuum of properties. This isn't a problem with our classification system necessarily. It's a reflection of how the universe actually works. Mass composition and formation history all vary continuously, producing objects with a continuous range of properties. When we talk about the largest planet ever discovered, we're implicitly drawing a line somewhere and saying that objects below a certain mass threshold are planets and objects above it are something else. But that line is somewhat arbitrary. The International Astronomical Union set it at 13 Jupiter masses based on the deuterium fusion criterion. NASA uses 30 Jupiter masses as a practical limit. Other astronomers use different criteria based on formation mechanism or orbital characteristics. The important thing is to be clear about which definition you're using, and to remember that the universe doesn't care about our categories. Let's talk now about the future of exoplanet science and what the next decade might bring. One of the most exciting prospects is the possibility of detecting biosignatures in exoplanet atmospheres. A biosignature is any signal that indicates the presence of life. On Earth, oxygen is a strong biosignature because it's produced in vast quantities by photosynthetic life and would disappear from the atmosphere within a few million years without continual replenishment. Other potential biosignatures include methane in combination with oxygen. Both gases react with each other, so their simultaneous presence suggests active replenishment. Phosphine, detected in Venus's atmosphere in 2020, though the detection remains controversial, is another potential biosignature because it's produced by anaerobic bacteria on Earth, and we don't know of abiotic processes that produce it in significant quantities. The James Webb Space Telescope is capable of detecting some biosignatures, particularly in the atmospheres of planets orbiting small, cool M-dwarf stars. The first results have been tantalizing but not conclusive. JWST has studied several potentially habitable planets, including some in the TRAPPIST-1 system, and has detected various molecules in their atmospheres. So far, no definitive biosignatures have been found, but the search is ongoing. Each observation teaches us more about what these worlds are like and refines our techniques for future observations. The challenge with biosignatures is that we need to rule out false positives, abiotic processes that could produce the same signals. Oxygen, for instance, can be produced by the photolysis of water vapor in a planet's upper atmosphere. If a planet is close to its star and receives intense ultraviolet radiation, water molecules can be split into hydrogen and oxygen. The light hydrogen escapes to space while the heavier oxygen accumulates. This could produce an oxygen-rich atmosphere without any biology. To confidently claim detection of life, we need multiple biosignatures that collectively point to biological activity and can't easily be explained by abiotic chemistry. This is where the study of massive planets continues to be relevant. By understanding atmospheric chemistry on gas giants, where we know there's no life, we learn what kinds of chemical reactions occur abiotically. We calibrate our models and our expectations. When we eventually detect a promising biosignature candidate on a rocky planet, we'll need to apply everything we've learned from studying gas giants, ice giants, and brown dwarfs to make sure we're interpreting the data correctly. Another exciting development on the horizon is direct imaging of Earth-like planets. The Habitable Worlds Observatory, still in the planning stages, aims to take actual pictures of rocky planets in the habitable zones of nearby Sun-like stars. This is extraordinarily challenging because Earth-like planets are incredibly faint compared to their stars. From 10 parsecs away, about 33 light-years, Earth would appear roughly 10 billion times fainter than the Sun. It's like trying to see a firefly next to a searchlight from thousands of miles away. To overcome this challenge, the Habitable Worlds Observatory will use a starshade, a specially shaped screen that flies in formation with the telescope, positioned to block the star's light while allowing light from orbiting planets to reach the telescope. The starshade needs to be positioned with incredible precision within about 1 meter, despite being tens of thousands of kilometers away from the telescope. The edges of the starshade are shaped like flower petals to minimize diffraction, the bending of light waves around edges, which could create scattered light that interferes with planet detection. If successful, direct imaging will revolutionize exoplanet science. Instead of inferring a planet's properties from indirect measurements, we'll have actual images. We'll see the planet's light reflected from clouds, oceans, and continents. By watching how the light changes as the planet rotates, we might be able to map surface features, distinguishing between land and water, between vegetated and barren regions. We might even detect seasonal changes as the planet orbits its star, watching vegetation green up in spring and die back in fall, if the planet has seasons and life. This might sound like science fiction, but the technology is within reach. Prototype star shades have been tested on the ground. The optical systems and detectors needed for the telescope exist or are in development. The main challenges are engineering, funding, and the political will to undertake such an ambitious project. But if humanity can land rovers on Mars, orbit a spacecraft around a comet, and build a telescope as sophisticated as JWST, we can do this too. The discovery of life on another world would be the most significant scientific finding in human history. It would answer one of our oldest questions and fundamentally change our understanding of our place in the universe. And the search for that discovery is driving innovation across multiple fields, from detector technology to atmospheric modeling to spacecraft engineering. Even if we don't find life, the knowledge we gain about planets, stars, and the conditions for habitability will be invaluable. Consider the journey of the atoms that make up a massive planet. Billions of years ago, those atoms existed inside previous generations of stars. When those stars reached the end of their lives, they exploded as supernovae, scattering their enriched material across space. This material, containing not just hydrogen and helium but also carbon, oxygen, silicon, iron, and all the other elements, drifted through interstellar space for millions of years. Eventually, gravity pulled it together into a new cloud, which collapsed to form a new star and its accompanying protoplanetary disk. In that disk, dust grains stuck together, building larger and larger objects through countless collisions. Some of these objects became the cores of giant planets, massive enough to gravitationally capture vast envelopes of hydrogen and helium from the surrounding disk. Over millions of years, the planet grew, sweeping up material and clearing a gap in the disk. It migrated through the system, pushed and pulled by gravitational interactions with the disk and with other forming planets. Eventually, the disk dissipated and the planet settled into its final orbit, a massive world 10 or 15 times the mass of Jupiter, glowing with the heat of its formation. This process, repeated billions of times across billions of planetary systems in our galaxy alone, represents one of the fundamental ways that matter organizes itself in the universe. Gravity pulls things together. Nuclear fusion in stars creates heavy elements. Planets form as a natural consequence of star formation. And within some of these planets, perhaps in their atmospheres or on their moons, chemistry becomes complex enough to give rise to life. It's all one continuous story, from the Big Bang to the emergence of consciousness. The study of massive planets fits into an even larger quest to understand cosmic evolution, the story of how the universe went from a hot, uniform soup of particles shortly after the Big Bang to the rich, complex cosmos we inhabit today. This story spans 13.8 billion years and includes the formation of the first atoms, the first stars, the first galaxies, and eventually the first planets. Each stage built on the previous one, adding layers of complexity. In the beginning, the universe was incredibly simple. Just energy, then fundamental particles like quarks and electrons, then the first atomic nuclei forming during the first few minutes after the Big Bang. For hundreds of thousands of years, the universe was too hot for atoms to form. Electrons and nuclei existed separately, and the universe was opaque to light. Then, as the universe cooled to about 3000 Kelvin, electrons combined with nuclei to form the first neutral atoms, mostly hydrogen with some helium and trace amounts of lithium. This moment, called recombination, allowed light to travel freely through space for the first time. That light, now stretched by the expansion of the universe into microwave wavelengths, is the cosmic microwave background we detect today. For the next few 100 million years, the universe entered a period called the Dark Ages. No stars had formed yet. The universe was filled with neutral hydrogen gas, with slight density variations left over from quantum fluctuations in the extremely early universe. These density variations were the seeds of structure. Regions that were slightly denser than average had slightly stronger gravity, pulling in more material. Over millions of years, these regions grew denser still, eventually collapsing to form the first stars. These first stars, called population 3 stars, were fundamentally different from stars today. They formed from primordial gas containing only hydrogen and helium, with no heavy elements. This made them incredibly massive, perhaps 100 or more times the mass of the Sun, and incredibly hot. They burned through their fuel quickly, living for only a few million years before exploding as supernovae. These explosions enriched the surrounding gas with the first heavy elements, carbon, oxygen, silicon, iron, and others, created in the star's cores and in the explosions themselves. Subsequent generations of stars formed from gas enriched with these heavy elements, allowing them to be smaller and longer-lived. These stars, called population 2 and population 1, are the stars we see today. Our Sun is a population 1 star, formed about 4.6 billion years ago, from gas that had been enriched by multiple generations of previous stars. The planets in our solar system, including the massive gas giants Jupiter and Saturn, formed from the leftovers of this star formation process. The massive exoplanets we've been discussing are part of this ongoing story. They're the latest products of billions of years of cosmic evolution, formed from material processed through multiple stellar generations. When we study them, we're not just learning about planets. We're learning about the history of matter in the universe, about how elements created in stellar cores end up in planetary systems, and about how gravity, chemistry, and physics work together to create the incredible diversity of worlds we observe. This perspective, seeing each discovery as part of a larger cosmic narrative, is what makes astronomy so profound. We're not isolated observers studying disconnected phenomena. We're participants in the story we're uncovering. The atoms in your body were forged in stars. The oxygen you breathe was created by massive stars that lived and died before the Sun was born. The calcium in your bones came from supernova explosions. You are quite literally made of stardust. And when you look up at the night sky and wonder about those distant points of light, you're experiencing a connection that spans billions of light years and billions of years of cosmic history. This connection brings a sense of both humility and wonder. Humility because we recognize how small we are in the vastness of space and time. The universe contains more stars than grains of sand on all the beaches on Earth. Our entire existence as a species, a few 100,000 years, is a fleeting moment compared to the age of the universe. Earth itself, 4.6 billion years old, has existed for only about 1/3 of cosmic history. In the grand scheme of things, we are tiny and brief. But there's also wonder and even a kind of empowerment in this realization. We might be small, but we're also remarkable. Against all odds, the universe has organized itself in such a way that matter can think, can be aware of itself, can look back at its own history and understand how it came to be. We are the universe's way of knowing itself. Every time we discover a new planet, decode the light from a distant star, or work out the physics of planetary formation, we're participating in something extraordinary. We're consciousness arising from matter, reaching out to understand its origins and its place in the cosmos. This is why the search for life beyond Earth matters so much. It's not just about finding microbes on Mars or detecting biosignatures on an exoplanet, though those would be momentous discoveries. It's about understanding whether this remarkable phenomenon of life, this ability of matter to organize itself into complex, self-replicating, evolving systems, is common or rare. If life is common, then the universe might be filled with other conscious beings asking the same questions we are, looking up at their own skies and wondering if they're alone. If life is rare, then every living world becomes infinitely precious, and our responsibility to protect the life we have becomes even more urgent. The massive planets we've explored in this journey are waypoints in that search. They teach us about planetary systems, about habitability, about the conditions necessary for worlds like Earth to exist and thrive. They push the boundaries of our understanding, challenging our definitions and forcing us to think more carefully about what makes a planet, what distinguishes formation mechanisms, and what role these giants play in the cosmic ecosystem. As our technology continues to advance, we'll find even more massive planets, perhaps some that push even closer to the brown dwarf boundary, or that exist in even more exotic configurations. We'll study their atmospheres in greater detail, mapping clouds and storms, measuring winds and temperatures, detecting new chemical compounds. We'll discover planets around different types of stars, in different types of orbits, at different stages of their evolution. Each discovery will add another piece to the puzzle, and eventually, if we're patient and persistent, we might find what we're really looking for: a small, rocky planet orbiting in the habitable zone of a nearby star. A world with liquid water on its surface, with an atmosphere that shows unmistakable signs of biological activity. A world where life has emerged, evolved, and perhaps even developed intelligence and technology. That discovery, when it comes, will be the culmination of centuries of scientific progress, building on the work of countless astronomers, physicists, engineers, and dreamers who dared to ask whether we're alone. But even if that discovery takes decades or centuries more, the journey itself is worthwhile. Every star we study, every planet we characterize, every mystery we unravel enriches our understanding and deepens our connection to the cosmos. We're living in a golden age of astronomy, with tools and technologies our ancestors could only dream of. We can see the echoes of the Big Bang, photograph black holes, detect gravitational waves from colliding neutron stars, and discover thousands of planets around other stars. These achievements represent the best of human curiosity, ingenuity, and collaboration. The massive planets, the super Jupiters and brown dwarf companions are reminders that the universe is more diverse, more creative, and more wondrous than we can fully comprehend. They exist at the extremes of planetary formation, testing the limits of what gravity and chemistry can create. They orbit ancient stars and young stars, single stars and binary stars, sun-like stars and red dwarfs. They have atmospheres of exotic chemistry, with clouds of silicates and metals, with temperatures ranging from hotter than lava to cooler than Earth. They might host moons that themselves are habitable. They might have formed through different mechanisms, some by core accretion, others by gravitational instability. They represent the full richness of planetary diversity. And here's the beautiful thing: we're just getting started. The exoplanet field is barely 3 decades old. The James Webb Space Telescope has been operating for less than 5 years. The extremely large telescope hasn't even begun observations yet. The Habitable Worlds Observatory is still in the planning stages. Future missions we haven't even conceived of yet will build on these foundations, pushing our capabilities even further. Your children or grandchildren might grow up in a world where we know of dozens of inhabited planets, where images of Earth-like worlds are as familiar as images of Mars are to us today, where the question of life beyond Earth has been definitively answered. That future is within reach if we continue to invest in science, to support curiosity-driven research, to educate the next generation of astronomers and engineers, and to maintain our sense of wonder about the universe. The massive planets we've explored today are part of that ongoing story. They're chapters in a book that's still being written, a story that began with the Big Bang and continues through to this very moment, with you reading or listening to these words, thinking about distant worlds orbiting alien stars. Every discovery in exoplanet science connects to a larger cosmic narrative spanning 13.8 billion years. The atoms in these massive planets were forged in previous generations of stars, scattered by supernovae, reassembled in new stellar systems. The same cosmic evolution that produced these giants also produced Earth and ultimately produced us. We are the universe's way of understanding itself, consciousness arising from matter and looking back at its own origins. This perspective brings both humility, recognizing our small place in the vastness of space and time, and wonder, marveling at the universe's ability to create complexity and beauty. The massive planets remind us that the universe is more diverse and creative than our imaginations. They exist at the extremes of planetary formation, in configurations we didn't predict, with properties that challenge our theories. Each discovery forces us to expand our thinking, to revise our models, to consider new possibilities. This is how science advances, not in a straight line from ignorance to knowledge, but through a winding path of discoveries, surprises, revisions, and deeper understanding. As we look to the future, we can anticipate more discoveries that will astonish and enlighten us. Perhaps we'll find planets even more massive than the ones we've discussed, pushing even harder against the planet brown dwarf boundary. Perhaps we'll discover habitable moons around super-Jupiters, worlds where life has evolved in the shadow of a giant. Perhaps we'll detect the first confirmed biosignature in an exoplanet atmosphere, answering the ancient question of whether we're alone. Perhaps we'll find something completely unexpected, a new type of planet or planetary system that we never imagined possible. Whatever discoveries await us, the journey itself is valuable. Every question we answer raises new questions. Every mystery we solve reveals deeper mysteries. This is the nature of scientific exploration. We're never finished. There's always more to learn, always another horizon to explore. And that's exactly as it should be. A universe completely understood would lose its magic. A cosmos with no more mysteries would be a diminished place. We're fortunate to live in an age of discovery, when new worlds are being found monthly, when our understanding expands with each observation, when the universe continues to surprise and inspire us. The story of the largest planets ever discovered is far from over. It's a continuing saga, with new chapters being written as you watch this video. Somewhere out there, a telescope is capturing photons from a planet we haven't discovered yet. A computer algorithm is analyzing data that will reveal a new super-Jupiter. A scientist is having an insight that will change how we think about planetary formation. The universe is vast and full of wonders, and we've only begun to explore it. If you've enjoyed exploring these massive worlds and learning about the cutting edge of exoplanet science, I'd really appreciate it if you could hit that subscribe button and give this video a thumbs up. It helps more people discover content about the incredible universe we live in. And speaking of incredible discoveries, if you're fascinated by what we're finding out there in the cosmos, you won't want to miss my previous video, where we explored something truly mind-blowing. The James Webb Space Telescope may have found Earth 3.0, but here's the shocking part: it might already be occupied. Head over and check out the video on the screen to dive into one of the most compelling potential discoveries of our time. The implications are staggering, and I think you'll find it absolutely fascinating.